The next shape that we're going to talk about is the cylinder, which is similar to the prism. And we should know that from our surface area unit, that a prism and a cylinder are similar to each other because they both have two bases. And the only main difference between them is that the bases on a cylinder are always circles, where the bases on a prism can change. You know, we could have a triangle, a rectangle, a hexagon, any of those shapes. For your cylinder, remember that this is a 3D solid with circular bases. That's what makes a cylinder a cylinder. And remember, we talked about in the last unit is that if I were to kind of take a cylinder and cut it down the edge and I lay it out flat, it's going to have a rectangle as that curved surface. And we had to reflect that with surface area with our pi, okay? Because it's not necessarily true rectangle when you lay it out flat, okay? But when we think about our cylinders, all of those things that we talked about from surface area are still going to be true for today when we're getting into volume, okay? So when we look at a cylinder, our formula for volume is actually very much the same as it was for a prism. So remember, our formula was base times height, where big B represented, remember, the area of your base shape, and H represents the height of the actual 3D solid. When you think about a cylinder, though, the shape we said was a circle for the base. How do we find area of just a circle? Pi r squared, right? So when you're dealing with a circle here, when you're trying to find area of your base shape, you're still going to have to think about this formula because we are still dealing with circles. So we're going to be using pi times radius squared. Now the height is really just going to be the height, but remember, this is going to be height of the cylinder . So that would be the space between your bases. So between the circles, that's the height, just like it was on a prism. Okay, now there's something called Cavalieri's principle, and I want to talk about what this is because you might see shapes that start to kind of look like this. This is showing you up here something called the stacking principle, and then down here this is getting into Cavalieri's principle. They're kind of similar to each other. The stacking principle basically just means like you could take a bunch of small circles, like really thin circles, and you could stack them on top of each other, and that's really what creates our cylinder shape. So they're kind of showing you like over here these like crackers or cookies, whatever they are. If they're all circular shaped, if I stack them on top of each other, they start to create a cylinder-like shape, okay? So when you have a canister, a circular canister that's filled with flat chips or cookies or crackers of some sort, like think about like Ritz crackers in their sleeve, they make a cylinder shape, right? Because all the Ritz crackers are in a circle. So that's kind of what that stacking principle is showing you, is that you've got multiple circles stacked on top of each other. What Cavalieri's principle says is that if you have a cylinder and it's maybe standing like upright, and then all of a sudden something happens to that cylinder that causes it to kind of lean over to its side, it starts to become tilted. Another word for that would be oblique. And you even saw this happen on your prisms homework from the other day. There was a problem that talked about the volume of a cube, and then there was another cube right next to it, but it was like slanted way over. And you should have seen that the volume of those shapes is not going to change at all. So even if the shape is standing upright versus being slanted over, that is not going to, for the most part, like overall, impact the volume of the shape. So Cavalier's principle, I'm going to just say it still works for cylinders. Oops. The only thing you need to check is that the bases and the height stay the same. So as long as the circular bases are not changing, like it's not getting wider or smaller, and as long as the cylinder's overall height is not getting any taller or shorter, then it should still be the same volume, regardless of which shape you use and how you plug it into that formula, because the radius should be the same and the height should be the same. Okay? All right, so we're going to start doing some examples. Remember here, though, from our formula up above, the base area is pi r squared. So if they give me the diameter, I need to make sure I cut that in half. If they don't give me my radius, because they give me the diameter, or they don't even give me the diameter, maybe they give me some other things, I might have to start thinking about, do I need to use Pythagorean's theorem? Do I need to use maybe sine, cosine, or tangent? You saw some of that on your prisms worksheet. So there might be things that we need to use in order to help us find these things. Okay, so let's take a look at this first one. So remember volume, I'm just going to write it up here along the top. Volume is, my B is going to be replaced by pi r squared because we're dealing with circle bases this time, times the height. So I need the radius and I need the height. Do I have either one of those for number one? We know the height for sure, right? What is the 6 representing? This is the diameter because it goes all the way across that circle. So what would be the radius? 3, right? We just cut it in half. So my radius here is going to be equal to 3. So when I go to my formula, it's going to be pi times 3 squared times height is 4. Okay, and sometimes I won't write it out like that. I'll just write it all out in parentheses like this, because that's all just one big multiplication problem. In the past, we haven't multiplied by pi. We're still going to keep that the same here. I don't really want to work with pi. So this would be how much? Good, 36. And then we still have pi, so keep that in your answer. And then again, how do we label volume? Good, centimeters cubed. Okay, any questions on that one? Okay, let's come over here to number 2. For this next one here, do we have the radius? Not outright. Okay, they're giving me the diameter again. This is your diameter. So what would be the radius? 2.5, good. Do we know the height? No? Where's the height at? Yeah, the height would be either like this side or it'd be this side of the cylinder, right? And they're not giving me either one of those. But think about what happens when we draw this in. I'm just going to outline my diameter, the height, and they are giving me this slant side here. It's a right triangle. What are we seeing? You guys are saying that this is 12, right? Because this is another one of those 5, 12, 13, those Pythagorean triples that we talked about. Okay, so my height is 12. Again, if you don't remember that, or you may be working with different numbers that maybe we haven't seen as much as the 5, 12, 13, you could always use Pythagorean's theorem. A squared plus b squared equals c squared, right? So my height is 12. So now we should be good to plug it into our formula. So volume is going to be pi times 2.5 squared times 12. What does that come out to be? $75, and then good, still pi centimeters cubed. Very good. Okay, excellent. All right, let's go on here to number 3. All right, just take a minute to look at that picture and think about what's going on. Okay, so if you're looking at this picture here, how many cylinders are in the picture? 2, okay. Are they the same? Are they different? What are you noticing? Yeah, the top one is obviously a little bit smaller than the bottom one, right? What's going on in the middle there? What do you think they're trying to represent in the picture by this thing right there? Yeah, it's like almost like it's being hollowed out. Okay, so think about almost like a roll of toilet paper. A roll of toilet paper is in the shape of a cylinder, but it's got that cardboard tube in the middle, right? So you can put it on the dispenser. And so when we think about this picture, I want you to think about this as like maybe the bottom is like the big roll of paper towels, and the top one is like a roll of toilet paper. So we'll have to think about the fact that there is this small circle here that we'll have to figure out what are we going to do with that? What are we going to do with that hollowed out piece? Okay. Let's start by just finding the volume of the individual cylinders because we know how to do that. Okay. So let's start with the small cylinder, the one on the top. And I'll just write here volume of small cylinder. What is the radius of this cylinder? Yeah, use these numbers down here. Okay, 10 is talking about the diameter all the way across, like here to here is that 10 that they have at the bottom of the picture there. So that's your diameter. What's your radius? 5. Good. So we'd have pi times 5 squared. What's the height of the small cylinder? Good, just 5. Okay, so what would this come out to be? Good, 125 pi. Very good. Okay, so that takes care of the small one. Let's move on to the big one. So I'm going to say volume of the big cylinder. What's the radius of the big cylinder? Good, 7, because it would be half of that 14. And what's the height of the big cylinder? 11. Okay, so that would end up being 49 times 11, which is how much? Good, 539, and then pi again, okay? Now, what would we do with those two numbers? If I wanted the total volume, we'd add them, right? Okay, so I'm just gonna write this down here. I would first start out by taking 125 pi, and I would add that to 539 pi. Okay, but notice I put that in parentheses. We're not completely finished here. We have that hollowed center that we need to account for. So let's just figure out how we would find the volume of just the hollowed middle piece. So I'm going to say volume of the inside. Okay, what would be the radius of that small hollowed out circle? 1, right? Because it's half of the 2. What's the height of the hollow piece? Yeah, it's 16, right? Because those are stacked on top of each other and they're stacked right where those hollow centers line up. So you want to find the total height of the entire shape, which would be 16. Good. All right, so then what does this come out to be? Yeah, just 16 pi. Try to squeeze it in here. I'm running out of room. 16 pi. Okay, so to finish this off over here, my small cylinder was 125, my big one was 539. We're adding those together. Should I add or subtract the 16 pi to represent that hollowed center? Yeah, we want to subtract it away because it's not in the shape, it's removed. Okay, if it's hollowed, it's not there, it's not filled in, so we want to get rid of it. Okay, so if we do this, what do we get? Good, 648 pi, and then still centimeters cubed. Very good. Questions on that one? Okay, there is a fourth one on this page, but you guys can actually cross it off. We're not going to do that one today. So that takes care of our notes for cylinders. So eventually we'll get to shapes like number 4. We're just not going to get into that yet today. So I'm going to get you guys your homework assignment, and you have the rest of the period to work.